Hello, everyone. Let's go through a more challenging example of the computation of a definite integral using the limit definition through the right theorem. So we want to compute the integral between minus 0.5 and 2 of 0.5 x cubed minus x squared plus 2. This is the infamous example that I love when I draw a function in general. It looks like that one. So the first thing to notice is that this is again a polynomial, and then a polynomial is continuous. So we can use the right theorem. And the first thing I like to do in a question like this is to label properly the endpoints. So here a is minus 0.5 and b is 2. Boom. So here we go. So we can use the right theorem because the function is continuous. It's a polynomial, so it's continuous. It starts at minus 0.5, so a is minus 0.5, and it ends at 2, so b is 2. So now we can do the 5 steps. This one is a bit more challenging, algebraically speaking, so you just have to be very careful. Step 1, the computation of delta x. So here delta x, boom, is 2 minus 0.5 over n, which simplifies to 2.5 over n. And in these questions, I find me personally, it is easier if I work with fractions. So 2.5 is 5 over 2. So I can write 2.5 over n as 5 over 2n. So my delta x is 5 over 2n. Step 2, the computation of xk, so the right endpoints of the kth subinterval. So xk is always a plus k times delta x. So in our case, boom, xk is minus 0.5 plus k times 5 over 2n, the delta x that we just freshly computed, which simplifies to, so again here, I'm going to work with fractions, minus 1 over 2 plus 5k over 2n. So that's my formula for xk. Step 3 is to compute f of xk's, which will be the height of the kth rectangles. So here, f of xk, so here you need to start with your function, 0.5 x cubed minus x squared plus 2, and you need to replace every single x by xk that was freshly computed to be minus 1/2 plus 5k over 2n. So if you do that, boom, f of xk is 0.5 times, in a bracket, minus 1/2 plus 5k over 2n. That's my xk to the power 3, minus, in a bracket again, minus 1/2 plus 5k over 2n squared plus 2. So here, I'm just taking my f of x and replacing every single occurrence of x by xk, which we know, because this is freshly computed, to be minus 1/2 plus 5k over 2n. Now the next step is to simply FOIL and simplify. So this is purely algebra. It's typically the toughest step for most of you, but it's just algebra. So let's just FOIL and simplify as much as possible. So here we go. So if you FOIL the power 3 and the power 2, this is what you'll get. Boom. Okay, so again here, I'm going to work with fractions. So the 0.5 is going to turn into a 1/2. Now, if you FOIL minus 1/2 plus 5k to the power 3, you're going to get minus 1 over 8 plus 15k over 8n minus 75k squared over 8n squared plus 125k cubed over 8n cubed. So FOIL it the way you want. I don't care as long as you do it correctly. Minus, so if you FOIL minus 1/2 plus 5k over 2n to the power 2, you're going to get 1 over 4 minus 5 over k over 2n plus 25k squared over 4n squared, and then plus 2. So that step was purely just FOILing the power 3 and the power 2. So we have a lot of terms. Now the next step is to combine the k's together. So all the constants, I will combine them together. All the terms that are multiple of k's, I'm going to combine them together. All the terms that are multiple of k squares, I'm going to combine them together. And all the terms that contain a k cube, I'm going to combine them together. But before doing that, I need to first multiply by 1/2 inside my first bracket, and I need to distribute the minus sign inside my second bracket. So if you do that, you can verify that you get the following computation. Boom. Okay, so I just multiply through 1/2, and this is how I got first my minus 1 over 16 plus 15k over 16n minus 75k squared over 16n squared plus 125k cubed over 16n cubed. And then if you distribute the minus sign, you get minus 1 over 4 plus 5k over 2n minus 25k squared over 4n squared plus 2. So just multiplication by 1/2, distribution of minus 1 or the minus sign. Now I have my equation. Now I want to regroup all the terms together. So this equation simplifies to the following one. Boom. Okay, so the way you get the simplified version is by doing the following. So first, you group all the constant terms together. So the terms that do not depend on any k. So for example, if you take minus 1 over 16, minus 1 over 4, plus 2, you're going to get 27 over 16. Now you do the exact same thing using the terms depending on k. So 15k over 16 plus 5k over 16n, plus 5k over 2n simplifies to 15k over 16n. Now, if you do the exact same thing for the k squared terms, so if you take minus 75k squared over 16n squared plus minus 25k squared over 4n squared, that will simplify to minus 175k squared over 16n squared. And then the last term, 125k cubed over 16n cubed. Well, it's just 125k cubed over 16n cubed. And that is the formula for f of xk, which is the height of the kth rectangle for the right Riemann sums from the first one to the last one. So k is just the index that labels all of them from the first one, so from k equal 1 to n. Now, step 4, the big step of those 5 steps, is the computation for Rn. Remember what Rn is? It's the area of the n rectangles using the right Riemann sum. So here, Rn is the sum of all rectangles from k equal 1 to n of f of xk times delta x, where we know what fk is, freshly computed here, and we know what delta x is, it's also freshly computed. So here we go, boom. So that's the Rn. So Rn is the sum from k equal 1 to n. Remember that summation just means we're adding all the rectangles from the first one to the n one. So that's what this sigma notation is. We're adding all rectangles from 1 to n, but we're doing this in general. F of xk, that's my step 3, times delta x, that's my step 1. And now the only thing you have to do is simplify. So the first thing I'm going to do is just distribute the delta x, the 5 over 2n, inside my bracket. So here we go. So if you distribute 5n inside the bracket, you're going to get the following thing. Boom. Okay, so your summation is going to become the summation of 27 over 16 times 5 over 2n. That simplifies to 135 over 32n. 5 over 2n times 55k over 16n will simplify to 275k over 32n squared. If you multiply 5 over 2n times minus 175k squared over 16n squared, you're going to get minus 875k squared over 32n cubed. And if you multiply 125k cubed over 16n cubed by 5 over 2n, you're going to get 625k cubed over 32n 4. So that's simply distributing the delta x inside the formula for f of xk. Again here, a lot of notation, just be careful. So then after distributing the delta x inside, I like to distribute my sigma inside my summation. So the sum of a sum is the sum of the sums. That sounds a bit weird, but if you just distribute the sigma, this is purely notational, but when you distribute the sigma, this is what you're going to get. So boom. Okay, so you're just distributing the sigma. So now the sigma is on top of everything. But this is very, very important because now what you can do for all those 4 sigmas, those 4 sums, you can factor out anything that does not depend on k, because now the goal is to get rid of those sigmas. useful. As long as the sigma is there, it means you're summing up n terms. You don't want to be summing up n terms. You want an explicit formula, sigma free. You want to be sigma free. So for the first, so if you factor out everything for all the sigma, this is what you're going to get. Boom. Okay, so the first summation, so everything can go outside, the 135 over 32n. So of course, be careful when you're factoring everything out, you're leaving 1 behind. For the second sigma, you can factor out the 275 over 32n squared. You're leaving inside just a k. And then for the third one, you can factor out the 875 over 32n cubed, leaving the k squared inside. And then for the last one, you can factor out the 625 over 32n 4, leaving the k cubed. And here the idea now is that we have 4 summation. You're summing 1 n times, you're summing k from 1 to n, you're summing k squared from 1 to n, and you're summing up k cubed from 1 to n. We have ways to get rid of those sigmas now using the Star Theorem. So here we go. After you use the Star Theorem, boom, okay, big explosion. But again here, this is just notation. There's not a lot of computation. If you're summing one, so there's no star formula for the first one, but if you go 1 plus 1 plus 1 n times, you're going to get n. So the summation of 1 from 1 to n is just n. The summation of k is n squared plus n over 2. I'm using my Star Theorem. The summation of k squared from 1 to n is 2n cubed plus 3n squared plus n over 6. And the summation of k cubed from 1 to n is n4 plus 2n cubed plus n squared over 4. Again, using my Star Theorem here. And that's your formula for Rn. Again here, it looks like a creepy formula, but it's really, really powerful. Like if, for some example, we're not going to do this in this chapter, but if, for example, you wanted to approximate this definite integral using 1,000 rectangles using the right Riemann sum, it would be crazy to do. But now what you can do is in this formula, what Rn is computing, it's a formula. It's an explicit formula where you simply have to replace n by 1,000 and you're going to get the right Riemann sum in one simple evaluation. It's so hot. This formula is so hot. It looks kind of crazy, but it's just so powerful. It's like you have the power in your hand to compute the Riemann sum for any n. Yeah, baby. Yeah. Now we're ready for the last step. Again, in those 4 steps, step 4 is always the craziest one. Step 3 is debatable, but step 4 is always the craziest one. Step 5, everything should be fairly direct. So here, now we want the exact value of the definite integral using the limit definition, using the right theorem. So we're just going to compute the limit of the formula that we just freshly computed in the previous step. So here we go, poof. So the integral between minus 0.5 and 2 of 0.5x cubed minus x squared plus 2 is the limit of Rn that we had, I'm not going to read it again, but that we had computed in step 4. And now what you do, because it's a limit going to infinity, and you're allowed to do this because we're going to get rational expressions in our examples, you just need to keep the highest degree term. So at the numerators, we're going to keep n. We're going to keep n squared. So we're going to keep n. Whoa. We're going to keep n squared, 2n cubed, and n4. And don't really care about the other terms because they will be insignificant as n gets larger. So this will simplify to the following limit. So poof. So we get this brand new limit. And of course, if things are done correctly, you will feel it. Like things will simplify nicely here. So you can see that all the powers of n, they cancel perfectly. The n over n squared over n squared, n cubed over n cubed, n4 over n4. This is when you know you've done the right job here. Now you're just dealing with constants. So here we go. Boom. So this limit is equal to 135 over 32 plus 275 over 64 minus 875 over 96 plus 625 over 120, 128. And this simplifies using decimal values to 4.28, 38, 54, 16, etc. it's a good exercise to compare this exact value with the approximations that we've done before. They're really close. Our approximations were already pretty close, but now we have the exact value. We pushed that process to infinity, and now we have the exact value of the definite integral of 0.5x cubed minus x squared plus 2 over the interval minus 0.5 to 2. Woo! So that's a big example. I must confess, I am aware this is a tough one, but this is the toughest one you'll ever get. Like here in this section, I have two examples. We did x squared between 0 and 4, which was probably the easiest example that you could do. And we have that example, which is the hardest. And typically in assignments or on a test, you will get something in between in terms of difficulty. So if you understand these two examples, the first one just to get acquainted with the steps, and then this one just to be acquainted with how hard it can get. But then on the test, you will get something in between. All right, for that example, that's it. So let me end this video with a very nice remark. In the universe of all functions, so things that you work with in a calculus course, if a function has a derivative, so if it's differentiable, then automatically it's continuous. And if it is continuous, automatically it's integrable. So integrable functions are like our larger class of function, but there are some examples of non-integrable function. But this is like crazy stuff. But for now, that's it. That's all. Bye-bye. Wow, oui, tu m'as fait peur. Wow, okay. Wow. Toi aussi, t'es tanné, hein? T'es-tu tanné? Okay, all right. Bye-bye, là.